Alrighty, happy Wednesday, everyone. Let's get through the problem set stuff first, and then we're going to move on to the classwork. So, if you are good and you talked about this as a table, then you can just kind of skip ahead. I would say that probably number 1 and number 2 are the most important. If you are having a hard time with those ones, then I would take a little bit of time and double check your work using this. But basically, we have CDs that cost $12 a piece, and then the company's charging $4.50. And so this is a lot like the classwork from yesterday, where you have. Hold on, let me get rid of the lightsaber. You have this expression shows $12 times the number of discs or CDs, and then you're always adding on that extra $4.50. So if you had 8, it would be 8 CDs times $12 a piece, and then you'd add the $4.50 for shipping and handling, $100.50. Number 2 is very similar, where you have books are $2.95 each, and then the shipping is always $4. So it's going to be $2.95 times however many books you have, and then you add $4 at the end. So it would look like that: $2.95B plus 4. This fun fact, or maybe not so, whatever. Fun fact: this little extra plus 4, those are actually called constants because no matter what is happening, right? This part of the expression, or this term right here, 2.95b, that value will always change depending on like how many books you're buying. So if you're buying one book, it's 2.95. If you're buying 2 or 3 or 4, that term's value actually changes, but you're always adding 4 onto the end, so we call that a constant. So looking forward to algebra. Number 3, same type of thing. You have $120 per week, and then you have the $450 that you had in graduation gifts. So you start off with $450, and then you're going to add on to that $120 per week. You can make your table using that, and I'll just show briefly the rest of this, long enough so you can pause it if you want to look at it. And I think that's it for that one. Okay, moving on to today. Okay, so this lesson's actually pretty cool. There's some interesting things that they talk about in this that you can actually look up later on. For this one, this first exercise, I'm going to help you get started on these, and then you can finish them on your own. Mrs. Penny has someone guest teaching today, I think, so you might need to be able to do math in a little bit less time, so I'm going to try and get this done quickly. Basically, for number 1, you need to predict how many times you could fold a piece of paper in half. And at the very end of this, I'll go back and say something about that. But anyway, so at the top of this table, we have 0 folds, would have a number of paper layers that result would be 1. You've got a piece of paper, not folded at all, it's in 1 layer. And we express that as 2 to the 0 power. And if you're wondering why anything to the 2 to the 0 power, hold on a second and I'll write something out. So basically, the reason that anything to the 0 power is 1 actually kind of comes into play and makes a lot more sense when you look at negative exponents. And we're not really working with negative exponents yet, but just so you know that there's an actual reason why it works out to 1. So here in the middle we have 2 to the 0 power is 1, and anything to the 0 power is 1 because if you start comparing, we all know that 2 to the first is 2, because that's 2 times itself one time, which is just 2. And then we know that 2 to the second would be 4, because 2 times 2 is 4. 2 to the third would be 8, because 2 times 2 is 4 times 2 is 8. And when you start looking at negative exponents, you find that it starts creating this neat little pattern where, 2 to the first is 2, 2 to the negative first power is 1/2. 2 to the second is 4, but 2 to the negative second is 1/4. It's not 4, it's 1/4. And whereas 2 to the third is 8, 2 to the negative third is 1/8. So it kind of ends up being like in the middle, is basically what's going on. So going back to the table, we can see that the number of folds would be one layer. That's like just one piece of paper right out here. That's one layer, and we can represent 1 as 2 to the power of 0. That'd be 1. Now, how did you get 2? Well, because if you continue this table right here, we can see that if you fold a piece of paper once, you have kind of like that first layer, and you have that second layer back here. And so there's 2 layers. That's 2 to the power of 1. If you fold it again, if you took this and you folded that again, then you get 4 layers, and that would be 2 to the power of 2. And then you fold it again, and you have 8 layers, and that's 2 to the third power. And so if you're having a hard time seeing how these layers are happening, just grab a piece of paper and start folding it. And you could count the layers as you're folding it. So you can continue this table to fill out the rest and answer these questions. And I'm going to start the next one for you. So bacteria, this one's about bacterial infections, or just, infections kind of sounds gross, but it's just how bacteria replicate using binary fission. And all that means is that you have a bacteria and it splits into 2, and that bacteria splits into 2, and then each of those bacteria split into 2. And that's how bacteria replicate. So if I continue this table on, I'm going to find that as you go down in generations, the bacteria is doubling. And we can continue this by writing this as a power using exponents. If I go way down here, I'm going to help you out with one of these. Now this says write an expression for how many bacteria would be present after G generations. So I have 2 to the G power. And you might be like, holy cow, what's to the G power? What does that even mean? Well, if you look up here, you're going to notice that the pattern, obviously this as in standard form is this, like 2 to the 6 is 64, yes. But more importantly, these are really just 2 different ways to write the same answer for the generations. Okay, but 6, how do you get from 6 to 64? How do you get from 4 to 16? You're actually doing this. And what you should notice is that these exponent powers are the same values as the generations. 5th generation, 2 to the power of 5. 6th generation, 2 to the power of 6. So this exponent actually represents the number of the generation. So if our expression should be 2 to the generation power, because whatever number we put here will actually tell us once we solve it, how many bacteria are in that generation. So, for example, if you wanted to figure out, how many bacteria are present in the 231st generation, it would be 2 to the 231st power. And that would be like the same as continuing this table all the way to 2 to the 231st, where this would be the 231st generation. So you can go fill in the rest of these. And lastly, we have this one. This can be a little bit confusing, but what they're doing is we're actually saying, and it says it in this problem, it says the box has a width, and the height of the box is twice the width, and the length of the box is 3 times the width. And what they're doing is, a lot of times what can help us solve problems is by only using one variable, figuring out a way where we can represent multiple things like the height and the length and the width, but using only one variable. So if I'm looking at this, we know that this red area right here, that could be like a rectangle. And so when you're finding the area of a rectangle, it's the width times the length. And so volume is similar to area, but it's kind of what fills a 3-dimensional shape instead of what fills a 2-dimensional shape. So for volume, you're doing the width and the length, which would kind of find the area of this flat portion here, but then you also multiply it times the height. So that's where this volume problem comes from that we're going to talk about. And the reason that they're saying these things right here is because, first of all, they're saying that we have a width, but then they're also saying that the height is the same as 2 times the width, and the length is equivalent to 3 widths. So imagine that the width was 2. We could know that the height is 4, because the height would be 2 times the width, which is 2. So 2 times 2 is 4. And then since the width is 2, then we could put a 2 in here and know that the length has to be then 6. So, but using our formula down here, that's exactly what they're doing. They're saying, the width is the width. They're going to say that the width is the width, but they're going to say that the length is the same thing as 3 widths, and the height is equivalent to 2 widths. And this helps us because we can kind of, first of all, if you can think of this expanded, so the 3W is the same as 3 times W, W is W, and 2W is the same as 2 times W. And then they kind of rearrange it, so we have 3 times 2 times the 3Ws. And then you could take these, right, and you can take, well, I know that 3 times 2 is 6. And I know that W times W times W is the same thing as W to the 3rd power. And so instead of having this longer volume equation, you could have the volume equals 6 times the width cubed. And that can help us because if you know what this one length is, you could solve for the volume of the entire thing in this case. So this is actually, the volume would be way down here since they have W. That's actually this. So the volume in cubic centimeters is 6 times the width cubed. And to do one of these for you, as an example, I'll do the second one. So this would be 6 times the width, and in this case, it's telling us that the width in centimeters is 2. So that would be 6 times 2 to the 3rd. I'm going to do this for you because you need to remember that exponents come before multiplication in order of operations. So first you have to do 2 times 2 times 2, or 2 to the 3rd, which would be 8. So this equals 6 times 8. And that equals 48. Alright, and then you could do the rest of them. If you finish early, I'm done, but if you finish early, here's something you can do. You can get started on the homework, and you can also, actually, fun fact, if you've made it all the way and you've listened, this right here, this whole little folds thing, is impossible to do, I think, more than 7 times. There's a whole Mythbusters episode where they talk about how no matter how big the piece of paper is, you can never fold a piece of paper more than, I think it's either more than 7 times. It's like you can fold it at most 7 times or no more than 7 times, something like that. But it has to do with the fact that the corners and the edges start to bunch up. So even if you had a piece of paper like the size of the universe, it wouldn't work. They got a whole giant sheet of paper that was the size of like an aircraft hangar, which is an enormous building, and they tried folding it, and it just didn't work. It was pretty cool. And this last one is actually, this checkerboard problem is, I'll actually, you know what, if you've waited this long, I'll help you get started. The checkerboard square, since there's 1 grain of rice on the first one, that would actually be, this is again the 2 to the power of 0. 2 would be 2 to the power of 1. 3 would be 2 to the power of 2. So notice that the power is 1 less than the checkerboard square. This is actually based off of an old, I think, a Chinese proverb in which some peasant or something did some crazy thing for the emperor, and the emperor said, "You can have whatever you want," and the peasant said, "You know, I want to have a checkerboard with 1 piece of rice on the first one, 2 pieces of rice on the second, 4 pieces on the next one, and double pieces of rice on every next thing." So it was like, 1, 2, 4, 8, 16, 32, 64, and it continued on throughout the whole board. And it turns out that he ends up the richest person in the kingdom because, in China, rice was used as a commodity or as kind of as money, and so he ended up with more rice grains than everyone. Pretty cool. Anyway, that's all. So, good luck. Have fun. See you later.